So in this problem, we want to determine where the function f of x is differentiable. And we're also going to use our calculator to help us differentiate. But first, remember that differentiable means that the curve is first continuous, and then also that the slope is smooth or equal on both sides of any type of point of interest or any point throughout the function where it's differentiable. If we look at this one that's not differentiable at 1, it is continuous, but we look, the slope this way is not equal to the slope this way, so therefore this function is not differentiable at 1. So if I look at this piecewise function, I see that less than 1, it's a quadratic, which is continuous and differentiable. And then here I have a line, which will always have the same slope, which will be differentiable and continuous. So I just need to focus on this piece right here to make sure, is it differentiable at 1? So before I can check if it's differentiable, it has to be continuous. Because if your function is not continuous, you can't even go into checking if it's differentiable at a place where a function value does not exist. So let's first check if it's continuous at 1. So the first part of checking continuity is, does f of 1 exist? So f of 1, I would use this top function to calculate that, is 2 plus 1 squared, just substituting in substituting in 1, and that is 9, okay? So it exists. So now 2, I need to check the limit from both sides. So the limit as x approaches 1 from the left of f of x, I would be just plugging in direct substitution in here, which is 9. And then the limit as x approaches 1 from the right of f of x would equal 8 plus 1, which is 9. So therefore, this means the limit as x approaches 1 overall of f of x equals 9. So then the third part of continuity that we must show is that f of 1 equals the limit as x approaches 1 of f of x, which equals 9. Therefore, f of x is continuous at 1. So now that we know that it's continuous at 1, and it's continuous less than 1, and it's continuous above 1, so it's continuous for all x not equal to 1. This we know from here, knowing that this piece is continuous and this piece is continuous. So this, just by definition of this function, we know it's continuous for all x values not equal to 1. So then we had to check this jump value to make sure that it's also continuous at x equals 1. So now that we know that f of x is continuous everywhere, we can check and make sure it's differentiable at this point here. Because remember, the limit might exist, but the slopes might be different on opposite sides. So all we've shown is that it's continuous. We have to make sure the slopes are the same all the way through this curve. So now we're checking for, is it differentiable at 1? Because anywhere around 1, below 1, and above 1, it will be differentiable. It's only here we need to check. So it's differentiable at 1 if the limit as we approach 1 of our derivative exists. That means that the slope from this side is equal to the slope of this side, not this. So let's see. F prime of x equals, let's see, if I take the derivative of this, I'm going to use it's going to be the derivative with respect to x of 2x plus 1 squared, and the derivative with respect to x of 8 plus x, and we're going to go ahead and evaluate those at x equals 1 with our calculators to make sure that those are the same. Now we'll also in the future practice calculating this by hand, but let's just practice this calculator skill that's a necessity for the AP test. So the first one we want to turn on, and I'm going to calculate. So I want my menu. We are doing calculus, which is number 4, and I want a numerical derivative at a point. The value is going to be 1, and I want the first derivative. Okay, my first function is open parentheses 2x plus 1, close parentheses squared, and let's see what that equals. So that equals 12. So now let's use my second derivative. This derivative of my second piece. So going to my menu again, down to 4, numerical derivative at a point, the value is going to be 1. Okay, and now my function is 8 plus x. And enter, and it is equal to 1. So what do we see about the slopes on both sides of 1? Well, this one equals 12 as we approach 1 from the left. This one equals 1 as we approach from the right. So limit as x approaches 1 of f prime of x does not exist. Therefore, f of x is not differentiable at x equals 1. So you would have to show all of these steps to come to this conclusion. You could not just figure that out in your head. You would have to show all of these steps on a free response question to accurately prove that it's not differentiable at x equals 1.